to go in. That is the... Everybody in the world touched the pad and it should be used. So I've got the, let's take a little... Morning crew and welcome to the Andy Mechanic YouTube channel. Now outside, under the canopy, I've got a side-by-side, an ROV we call them now here in New Zealand. And it's got a fault code on the dash, fault code 46, which is telling me there is some kind of charging fault. Now it might be an overcharge situation, it might be an undercharge situation, it may be a no charge situation. I don't know, we have to go and check. Now for most people we don't have access to the Yamaha diagnostic equipment, which is only used by Yamaha dealers. They've only got access to that, and you may not even have the service manual. If you don't have the service manual, you don't really have specs, and that can cause a bit of a problem. But we do know that a standard 12 volt system, you know, like on most cars and quad bikes and motorcycles and that kind of thing, tend to have a set point voltage of about 14.5 to 14.6. That's the charging rate, you know, with the engine at fast idle, 3, 4, whatever thousand RPM, depending on where the red line is. So a fast idle setting, the voltage across the battery should be, once it's fully charged and all the lights and stuff are turned off, should be around about 14.5 volts. On that Suzuki GN that we worked on a while back, Suzuki told us it was supposed to be 15 volts, which is the highest I've ever seen. But hey, you know, Suzuki write the manual, they make the bike, they tell us what the specs are, and I was a bit surprised, but it worked. Years ago, when lighting electrical systems on motorcycles and cars, motorcycles especially, there was quite low demand. They had little batteries and only a few lights, and the headlight didn't use very many amps, and the ignition system was very simple. The windings in the stator were made of much thinner wire, which meant they had a slightly higher resistance, and we could basically test them back then with an old analog meter like this one, because you know the specs would be, well, to give you an idea, what have I found out this morning? Well, we've got what is it, 1997 YFM 350 was 0.7 to 0.86 ohms, so it was still under an ohm, which is actually quite hard to measure with a meter, not very accurate. We've got an old Kawasaki Sherpa, 0.4 to 1.1, you know. But now on the newer vehicles, which have got a lot more electrical systems, the output from the charging system, you know, in amps needs to be much higher to cope with running all those systems. You know, we basically have liquid cooled engines nowadays. They have cooling fans. Those fans use quite a considerable amount of current, so that current's got to come from somewhere. It doesn't come from the battery because it would go flat eventually. It comes from the charging system. Once that engine's started, all the power, the electrical power to run the electrical systems on the vehicle should come from the charging system. Anyway, enough about that. Now, you probably remember that old Nissan Patrol that I still have. I've got some welding to do on it. Well, we did a video on testing the internal components of the alternator on that vehicle, and actually, believe it or not, this is the stator out of the spare alternator. And when we came to test this in the video, I was looking through the Nissan manual for that vehicle, looking for a resistance value, and it didn't give one. It just said, if there's continuity, it's good. And that's probably because you'd need a milliohm meter to test this, because the wires are really fat. So the resistance is going to be next to nothing. And you wouldn't even be able to use a standard multimeter to test something like this, not accurately. These multimeters really only measure down to 1 decimal place on ohms, and that's not good enough. On this ROV, I've done some research, and the specifications for the stator in this unit are, where are they now? Let's have a little look. 0.09, so that's 0.09, extremely low, ohms, to 0.13. That is way too low to use one of these meters to test. It's just not going to work. So we're going to have to come up with an action plan, because it's quite common for these stators in this particular model of ROV to fail, unfortunately. And to give you an idea what they look like, this is a stator. It's extremely similar to the one that's in this vehicle, and this one has failed, but there's nothing visual to indicate that it's burnt or damaged. Everything looked great on it, and if you're asking, that's the pickup there for the crank angle sensor. So there you go. That one looks fine. Yes, I've changed a few of these. Here's another one. Now this one does look a lot more blackened, as you can see. Look, compare the two. Very different in colour. And if you could smell it, you'd be able to smell it was burnt. And then if you look in here, you'll see, just try and get it in focus for you. You'll see here, this area here is all burnt. This is where the short has been taking place on that winding there, look. And that obviously is extremely bad. And then there's another case. This one, I think it hasn't shorted out, it's just overheated, because these things rely on engine oil to keep them cool. And of course, if the engine gets too hot, maybe the cooling fan for the radiator fails, the engine gets really hot, the oil gets really hot in the engine, and of course then the stator will start to overheat as well. So you can have a problem where it then starts to degrade the insulation, the very thin sort of lacquer type insulation on those winding wires. So anything that comes out looking like that is probably either failed or going to fail very shortly. Right, okay, so like I said, the vehicle's outside. We can't use a normal multimeter to test the stator winding. So we're going to test a battery, going to do the battery charging voltage first. And then we'll do an AC voltage output from the stator. Now that's usually around about 90, 105, somewhere around about there, volts AC on each of the three wires. So you just pick two and, you know, get a reading, fast idle, and then pick another two and take a reading, and then pick the last pair and take a reading. But we'll go through all that. But when it comes to testing the stator windings for resistance, I don't have, sure I could go out and buy one, a milliohm meter, and that gives you a really accurate resistance reading in ohms, obviously, down to usually about 3 decimal places, which will be excellent for testing the stator winding in that ROV outside. But I haven't got one, and they're about 400 New Zealand dollars minimum. That's the cheapest one I could find. 375 plus GST it was, so slightly over 400 bucks. You can go out and buy a fluke meter, which is about 1,000 New Zealand dollars. I'm not prepared to spend that kind of money, and obviously you guys wouldn't either, because you just say, hey, I'll just change the stator regardless if I think it's a bit dubious. So when we come back a bit later on in the video, I'm going to show you a method which is reasonably accurate. It's a lot more accurate than trying to use something that really only gives you 1 decimal place. I'm going to show you a method of how we can test that stator, that really low resistance of the windings in the stator, by using standard workshop equipment. That's the whole key to this video. Right, let's go outside and do that. We'll do an OCV first across the battery, open circuit voltage, with the ignition turned off. We'll disconnect the earth wire, get a battery voltage, and then we can then see, you know, we've got a starting point for the battery voltage. We'll start the engine up, fast idle, and see what we get as regards to charging rate voltage. Right, was that everything I wanted to cover? Yes, I think it was. Right, so I'm just going to disconnect the earth wire, if I have the right size spanner, hopefully. How's it? Oh, look at that, bloody good. Okay, so we can do an accurate LCV. Now, you can get away with, you know, with this unit there's no draw on the battery when the ignition's turned off, but or there shouldn't be, but just to be absolutely certain, a proper open circuit voltage. check is with the battery disconnected. You've only got to disconnect one of the two wires, and as you know, you always disconnect the earth first. Well, that's what the textbook says anyway, because most vehicles are negative ground these days. Right, okay, let's get rid of that wire. There's your ground wire. Stick that down there. Okay, so we need volts. There we go. I'll stick that down there in the middle so you can see it. Hopefully it'll stay there. And I've got some little jumper wires just so we can connect onto the battery terminals correctly, because I haven't got the little clips for my meter anymore, they broke. Right, that's that one and ground. Okay, so what have we got? We've got 12.73. Well, that's a fully charged battery. That's actually pretty high. Normally about 12.6 is fully charged. So maybe there's a bit of surface charge on the battery, although it hasn't been taken out of the vehicle. So, that could be a clue. Right, let's put the earth wire back on, get this thing fired up, and see what kind of charging voltage we're going to get. It's always fun working around the camera. Everything's covered in grease, just to make it even easier. No corrosion though. Once I fix this vehicle, it's going down to live in Napier, of all places. So it's got a long transport ahead of it. Yeah, I wouldn't normally do that, but I actually can't grip the nut. There's so much grease on it. Right. There we go. That'll do. Okay, multimeter back in position, and you can see the screen, can't you? Good. Okay, positive pickup back on, and negative. Right, perfect. Well, didn't change much at all, did it? Okay, let's get the machine fired up, and I'll do a fast idle, and we'll see what we get. Oh wow, look at that, almost 18 volts. Maybe it was over 18 volts, I couldn't quite see because, you know, I was away from the vehicle, away from the camera. So that's way, way higher than the 14 and a half, or even 14.6, what we call the set point voltage, which is the maximum voltage the battery should be supplied during a charging sequence. So we've got an overcharge situation. Right, we're finished now at the battery. Geez, that was noisy. Okay, so we got, near as damn it, what, 17.8, maybe more volts. I've not even looked at the video footage because, to be perfectly honest, 17.8, way too high. And if that vehicle was continued to be used with that fault on the charging system, it's initially going to cause damage to the battery. It's going to cause it to overcharge. These are sealed batteries, but they do have a pressure relief valve on them, so the battery's probably going to swell. It's going to get rounded sides, it's not going to be very happy, and ultimately that pressure relief valve will blow and a lot of gas will come out of the battery, and of course the electrolyte level will drop. These are a lead acid battery on these vehicles. But also it's going to cause the electrical systems on the vehicle to run at a much higher voltage than they should do. It's going to cause potentially damage to your ECU, maybe to some actuators on the engine as well. It probably won't damage the sensors because they're supplied a 5-volt feed from the ECU. So that tends to regulate that voltage. But ultimately it's going to cause problems. Now the question is, why is it overcharging? Is it overcharging because of a fault with the regulator rectifier, or is it, the regulator rectifier unit is a single unit. It's not inside the alternator like on a car. Usually it's a separate box on the vehicle. It has the regulator inside and the rectifier inside. The rectifier converts the AC current from the stator into a DC for charging purposes. And the regulator is the part that's responsible for regulating that set point voltage. So it could be the rectifier unit that's at fault, but we can't test that. You need a specialist piece of equipment to test regulator rectifier units, and because it's an integral component, it's all sealed up. I may not even be able to test it at all. I know I don't have any test equipment for that. Very specialists, but what we can do is we can test the voltage output from the 3 stator windings, and we can test the stator winding resistance, and we can also check to see if any of the stator windings have gone down to ground, if any of the insulation on those windings has got damaged, like in the examples that I showed you earlier on, and the winding is now touching earth. Now that is a problem, and that causes shorting and all sorts, and a tremendous amount of heat, because there's still current being made or being induced into that winding, and of course then it goes to ground and everything gets really hot. Too much waffle. Okay, out to the vehicle, and we'll do the AC voltage output test first. Here we go. Right, so I've removed all the gubbins to get down to these connectors. There's normally an air box in this area here, and on this particular vehicle we've got the 3 stator windings are here. They're white, and 2 go into one plug, and one's all on its own. And basically all these 3 wires back at the stator do eventually connect together. So we've got to unplug these if we can. There we go, that's 1. 2. Now I just need to find, here we go, look, use one of these. Let's grab some of these so I can actually basically probe from these plugs. So I'll get 2 more of these little connectors, and then we can connect our multimeter onto there. Okay, 1, 2. Now do bear in mind that out of here can be up to 100 volts AC, so you've got to be a little bit careful. You might get a bit of a shock. Right, let's get the meter set up for you so you can see what's going on. Come back, all is forgiven. Poor meter. Right. Okay, so we want to be on volts AC, and we know it's going to be around about 100, so that should, there we go, look, 1 decimal place, 3 before, that should give us what we need. Right. Now it doesn't matter which of the 3 windings we connect the 2 leads to, but we need to make sure that these leads don't short. So I'm going to post one down the air intake, because that's made of plastic, just so it doesn't touch the ground. Right, so we'll put that one on there, look. That's that one. It's really important they don't touch ground. The other one can go on the floor because that's made of plastic. And we'll stick that one onto the other winding there, look. So we do the 2 in the plug first. There we go, that should work. That's not touching anything. And they're not touching each other. There we go. Right, now we start the machine up again. And fast idle. Now I'm sorry about the vibration, it's probably going to juggle the camera around a bit. almost 72 volts AC, which to me is a little bit low. Oh, go back on there before we forget which one that one came off. There we go. And we'll go on to that one now. So we're doing the right hand one to you, and the one in the single plug. Hmm, 66, that's way low. Okay, and then we'll just swap the yellow, which is the ground, makes no difference. Yellow, yes, the ground, stick it on there, onto that one. And now our final test, here we go. Okay, so that was almost 66, so we are way down on AC volts output from this stator on all three of the windings. Now, okay, so the next test now is we've got to go and check the resistance of these windings. But we don't have a special meter to do that because the resistance value, don't forget, the specs for this stator is 0.09 to 0.13 ohms. And this ohm meter, if we stick it on ohms, which is under there, I think, there we go, look, we only get 1 decimal place. In actual fact, it's actually measuring the ohms now, and well, we've got 0.4, but we've got lots of wires and stuff in circuit and lots of bad connections, so let's not worry about that too much. But this ohm meter won't do what we want it to do. It's not accurate enough. Right, let's go back into the workshop and have a little chat. Okay, so we did the battery check, battery OCV, and then we did the charging rate voltage way too high. So we went down to the stator and took some stator AC voltage output readings, and they came out as being way too low, between sort of 65 and 78 volts AC. And I was expecting to see at least 90 volts AC plus. We can't test the reg rectifier, so we've got to basically check the stator. If the stator seems to be good, then we will just replace the reg rectifier, assuming that all the wires between these components are in good order and there's no shorts to ground or broken wires. So that's just standard stuff to check, and I'll be doing all that off camera. Okay, so the crux of the video is the fact that we can't test the resistance of those windings on the stator using a normal multimeter. It's not accurate enough. So what are we going to do? We can't go out and buy a 500 to 1,000 New Zealand dollar milliohm meter. That's just too expensive, and it's just, you know, you probably only ever do this job once in your life. It's not worth doing. You may as well just buy a new stator. They're about half the price. What we can do is put in a shunt. And now a shunt is a known value resistor, and we can look at the volt drop across that known value resistor and then look across the volt drop of whatever it is we want to measure the resistance of, and then because we know the volt drop of that one, we can actually do a calculation to work out what its resistance is. Now, this is not going to be as accurate as using a $1,000 milliohm meter. Not a chance, but it's actually a lot better than using, or trying to use, a normal multimeter. Right, there's a little diagram, a little circuit diagram to do, and some calculations. So you're going to need a calculator. Now, this is a scientific calculator. I have no idea how to use most of the buttons on this thing, but you just need a standard calculator. You can even use the calculator on your phone if you want. Okay, let's do some numbers and things. Here we go. Okay, sorry for the condition of my piece of cardboard, but it works. Right, now a very simple diagram. We're going to have our known resistor, and we'll call that R1, and that's going to be in circuit in parallel to a second resistor. Now the second resistor, believe it or not, is one of the pairs of windings, you know, two of the three wires from the stator, and we'll call that R2. And we're going to supply, ideally you'd supply this with 5 volts, but you guys probably haven't got a 5 volt supply, so we're going to supply it with 12 volts. 12 volts plus, and this is going to be down to ground, to earth. Okay, now resistor 1, like I said earlier on, is going to be a known value, so we're going to use a 220 ohm resistor. Now this one, to test our theory, before we go outside and take the readings on the stator, test our theory and to prove the equation, I'm going to stick a 10 ohm resistor in here, just for the test. Once we go outside and do the stator readings, this 10 ohm resistor will be replaced by the stator windings. Okay, now we have an equation. And the equation, oh sorry, there's a bit more to this actually. So we're going to take the voltage reading, once there's current flowing through this circuit, we're going to take the voltage reading of, or the volt drop, should I say, over this resistor and over this resistor. And that's going to be V1 and V2. All make sense so far? Hope so. Right, our equation is V2 divided by V1 divided by R1, close bracket, and that equals R2, the resistance of whatever's here. Okay, so let's set this little rig up, for real, produce the circuit, and take some readings, and see if our equation is going to give us 10 ohms. Wow, if it does, we know we're good to go. Right, so to build this little circuit, you're going to need a 220 ohm resistor, and I bought those yesterday, and I bought, I think it was 8 in the pack, yes, packet of 8, and it was 70 cents New Zealand, so they're very, very cheap, so you can afford to buy a few of them. They're good things to have around, very useful for this kind of thing. So we bought some of those, and at the same time, and they're not in the bag anymore, put them back in the bag, look, there we go, I bought some 10 ohm resistors as well, because I knew I was doing this. Right, okay, so from those, I produced this little circuit. Very simple. We've got the 2 resistors, and for the camera I've put some yellow paint on the 10 ohm resistor because it's real hard to see the colour bands. This is the 220 and this is the 10. Right, so we'll pop that down there. That's basically as it is on the diagram. We need 12 volts at this end and we need a ground at this end, and then we can measure the volt drop across the two. Here we go. Right. Power in. There we go. Good connection. And where's our ground? Here we go. Now I've chosen 12 volts because, well, you can use your battery on your car, can't you? You could use 9 volts. It makes no difference. Use a 9 volt battery if you like, little one. Okay, so now we can turn on our 12 volt supply. And I've just got a multimeter on there so I can accurately get it set. Just setting the meter. There we are. Bang on 12 volts. Okay, so all we now need is another multimeter to record the volt drop across each of these 2 resistors. So we're going to measure V1 first, and I'll do it on cardboard so there's no risk of any false readings coming through. And we've got 11.49 volts. Okay, so let's make a note of that. V1 is 11.49 volts. Okay. V2, that's across the 10 ohm resistor. Okay, so we've got 0.52. V2, 0.52 volts. Okay, and in total, because the two should add up together, yeah, 12.01. There's, damn it, isn't it? 12.0. Yeah, 12 volts. Perfect. Right. We need to do a calculation. So, we've got the equation, and the equation is V2 divided by V1 divided by R1 equals R2. Right, we can put some numbers in now, can't we? So V2 was 0.52, so 0.52 divided by V1, which is 11.49 volts, divided by R1, which we know is 220 ohms. 220 ohms. Okay, well, this bit's in brackets, so we've got to do that first. So, turn on the old crankulator, and we've got 11.49 divided by 220. Right, so that bit is 0.0522272. That'll do. 727, so 73. We'll round it up. There we go. Okay, so we've got 0.52 divided by that. Right, so R2 equals 0.52 divided by 0.0522273 equals 9.9, let's round it up, 6 ohms. Cool. That is a good result, because these resistors, don't forget, they, in fact, what are they? Let's have a little look. What's the tolerance on it? 1%. You see on there, look, it says little 1% on there, so that's plus or minus 1%. So it can be, you know, whatever 1% is, which will be 1% of 10 is 0.1, so it could be 9.9 ohms to 10.1 ohms will be the acceptable range of that. We've got 9.96, so bloody good. What I could do, if we really wanted to, and the reason why I haven't is due to meter accuracy, is if I disconnect all that. Now we know that the one with the yellow on is the 10 ohm resistor. So if I get the meter again, and we actually measure the resistance of that, this is why I didn't do this, because these meters are not particularly accurate, I don't think, down at this sort of range. So that's our 10 ohm meter, and we've got, wait for it, if you can see that on the screen, 9.9 to 10. 9.9 to 10 ohms. Perfect. Well, that all tallies, doesn't it? Oakley dokley. Right, so we've proved the equation works. Hopefully now you've got an idea of what's going on when we do the test on the vehicle. What I've done to help us is I've got another one of these 220 ohm resistors, and I've just soldered it to, I've just soldered it onto a couple of crocodile clips. So now it's really easy to put in circuit and really easy to take our volt drop readings. Okay, I think it's time to go out to the vehicle. Right, not easy. Okay, so we've got, this is our 12 volts in on the white wire. We've got our little tiny 220 ohm resistor, and we're going to connect that to one of the 3 stator wires. Okay, now this is our ground. I'll stick that one on there. So now we have a circuit, just like in the workshop on the bench. We've got our first resistor, 220 ohms, but our second resistor, R2, isn't a 10 ohm resistor anymore. It's actually running through the windings of the stator and coming back. So we'll be able to take some volt drop readings between across here, so that'll be V1, and then we can take a volt drop reading across here, which will be V2 across these two. So I've got the one out of the workshop, and I'm just going to turn on the power supply and calibrate our 12 volts again. Oh, bang on, look at that. Okay, so we can take some readings. We've got quite a few readings to take here, because there's going to be V1 and V2 for each of the 3 windings. Right, there's our little master crib sheet, and that's why I'll be putting all the information. Okay, here we go. Right, so first of all, V1 for winding 1. Okay, so positive on that side. How are you going to see this? Let's see if we can work it out. Maybe I'll get another zip tie. Maybe it'll balance. We'll let me see. Okay, what have we got? Jeez, it's not much, is it? 11.98 for V1. Okay, so we've got a 12 volts, so we should only have a very small volt drop across this winding. The actual stator winding itself. Oh, don't do that, come back. Okay, what have we got? Right, that's in millivolts, 5.9 millivolts. Jeez, okay, make a note of this, millivolts. 5.9 millivolts. Okay, right, let's just switch that across now. Put that one on that winding. So this will be winding 2. And take the same readings again. And they should be, if they're all the same, they should be the same. There is, damn it. Right, so this is V1 for winding 2. Yep, 11.97. Okay, 11.97 volts. And across, this is voltage 2. What have we got? And again, we're in millivolts. 5.9 millivolts. Okay. Send me before 5.9 millivolts. Now remember, these 2 voltages should really add up to our supply voltage, but there's we've got all these wires and stuff in the circuit as well. So I've just moved across the resistor now onto this one and left. So power 12 volts in is going in here, and it's returning back to the power unit via this winding. Okay, so volt drop again across .97. Okay, last reading, which is across there and coming out. What have we got? Again, it should be millivolts. 5.9 millivolts. Cool. Right, turn the power supply off. 5.9 millivolts. Okay, we've got our results. Let's go back in the workshop and do some sums. Right, time to do some calculations. Now they're all going to be about the same. So V2 voltage reading was 5.9 millivolts. So to convert that into volts, which we need for the equation, I've divided it by 1000. Okay, so our equation is, just to reiterate, is V2 divided by V1 divided by R1 close bracket equals R2. So whatever the voltage was at voltage 2 divided by voltage 1 divided by resistor 1 value equals R2. Well, this is bloody easy. Okay, so voltage 2, V2 was 0.0059 volts divided by voltage 2, which is 11.98 volts. Oh, remember the bracket. Divided by resistor 1, which we know is 220 ohms. Close brackets equals R2. Right, we've got to do the bit in the brackets first. So, get the old crankulator out. 11.98 divided by 220. Okay, so that's 0.054445, and it goes on forever, so it's recurring, is that? Right, that's that bit done. So it's going to be 0.0059 volts divided by that number there. Right, we're not far off. 0.0059 divided by 0.054. Yeah, 0.054. That's right, isn't it? Yes, 545 equals. Okay, so R2 equals 0.108 ohms. What was the spec? Spec was 0.09 to 0.13. Wow, that's in spec. So winding 1 is a pass. Right, and I think, judging by all these numbers, they're all going to be the same. The only difference is V1 drops to 11.7. So we'll do one more. We'll need to do one more calculation because windings 2 and windings 3 are exactly the same readings. So we'll do one more. A little bit of cardboard. Here we go. Okay, so V2 divided by V1 divided by R1 close bracket equals R2. Okay, so this time V2, oh, it's still the same, 0.0059 volts divided by V1. That's what changes, 11.97 this time. 11.97 volts, bracket. R1, resistance 1 was 220, close bracket equals R2. Got to work that bit out first because it's in the brackets. 11.97 divided by 220 equals, slightly different number, good, 0.054409 will do. So 0.0059 divided by that equals R2. Here we go. 0.0059 divided by 0.054409. Oh, nearly down at the same, 0.108, which is also a pass. Ohms. There you go, look. So windings 2 and windings 3. Wow. Well, that works out really well. That's the first time that I've had to do this test, because the older ATVs, the older ROVs, especially ATVs, older motorcycles, the windings in the stator are not, they don't have such a low resistance value. They're not such thick wires, and you can tend to get away with using a normal meter, you know. But now we can't. So I had to devise a different way, and it's called using a shunt. And that little 220 ohm resistor is the shunt. Okay, it's not 100% accurate, but our reading fell pretty much bang in the middle, or very close to the middle, of spec. So it leaves a little bit of tolerance either side. So I think it's pretty fair to say that that stator is fine. There's nothing wrong with it. It doesn't need to be changed. But there's one more test we have to do. We have to make sure that none of those windings have gone to ground, that the insulation around the windings, that varnish type insulation, hasn't got damaged and it's not shorting to earth. And that's a very simple test. We can use our continuity tester for that, and we just go between each of the 3 wires and the engine ground, you know, just somewhere on the engine is fine. And if we get a beep or we get a resistance, we get any kind of continuity, any kind of continuity, any kind of reading, then we know that there's something not right. It should be completely open circuit. Okay, let's whiz outside, do that, and then we can sign off. Here we go. Right, meter's set up onto continuity test. It should make a little beep if there's continuity. Hang on, press it again, hang on, there we go, select. That's the one, I think. There we go, look. So we get continuity, we'll get a beep. I'll do. Okay, right, I'll put the earth, the black wire, via a little link wire onto ground. So it's just going to go onto the engine casing there, look. And I can touch the engine casing just to make sure we're all good. There we go, perfect. Right, now just getting our stator windings. All we have to do now is touch each of these, and none of them should have continuity to ground. That looks pretty good to me. All open circuit, there's no resistance reading whatsoever. Okay, so we've tested our stator and we know it's fine. Wow. Okay, well I was really looking forward to doing this video, and I wanted to make a good job of it really, because I think this kind of test is going to be really useful to lots of people that don't have access to a milliohm meter. And it's not expensive. I mean, you know, okay, you need a standard multimeter, but really, you got to have one of those. And I use this amp clamp meter specifically because, you know, it's not really a proper multimeter as such. Its main function is as an amp clamp for recording, you know, high current flows on starting systems and stuff. But it did the job, and we've got the equation, and it didn't take me long to do a bit of research to sort of make sure what I was saying was right. And as regards the cost, you know, a few cents rather than spending a ton of money on a specialist meter. So we now know, provided all the wiring integrity checks out, and we know that the wiring to the stator and stuff is all fine because I've just been testing it all. We've got the wiring from those plugs up to the reg rectifier unit, which is at the front of the vehicle. And I think it has an earth onto that, and it also has a battery feed, so it can sense battery voltage and decide, you know, how much current or how much voltage to produce. So I hope you found the video helpful. I found it really helpful doing this because it's helped me too, actually. Assuming all the wiring's good, we're going to replace the reg rectifier unit, and fingers crossed that unit be all good. There will be a second video because I'm going to have to order that reg rectifier unit, and unfortunately, well actually fortunately, it's Christmas time and everywhere's closed, and you know, I can't get the part until early January. So there will be a second video where we install the reg rectifier unit and do a final set point charging voltage test just to see if I've managed to fix it. Okay crew, well if you enjoyed the video, why not click on subscribe. You'll see a little gear icon turn up. Click the gear icon and then you can tick the box to turn on notifications. If you're on a smart device, then it's just a little bell symbol on there. Just click on the bell symbol or touch the screen with your finger, and you'll see some little sort of, you know, movement lines around the bell, and that tells you that our friends down at YouTube are going to send you an email as and when I upload any new videos. Now, you'll also find me on Facebook, Instagram, Google+, and Twitter. Feel free to communicate through any of those portals, but please, first point of contact through YouTube, on the YouTube comments. That's where the videos are, and that's where the majority of the comments are. And if you ask a question that somebody else has already asked, you might see the answer further down if you scroll down. Although I do appreciate some of the videos now, I've got a lot of comments on them, so you know, I'm not offended if you ask the question again, it doesn't matter. I can't always get back to every question. I'm a pretty busy chap at the moment, and in all honesty, I've got a lot of videos to make for you guys, so busy making the videos like I am now and editing them. That takes time, and I've got to get back to work to Yamaha on the 3rd of January, so I'm against the clock a little bit. I've got a lot of jobs to do. Okay crew, well, Merry Christmas, have fun, and hopefully I've shown you an easy way of testing the resistance, the very low resistance of a winding, in this case a stator winding, using a shunt. Alright chaps, cheers, over and out.